Hello friends, in this video we will study about the memory map and the addresses in the microprocessor. So let's start with our topic. In 8085 microprocessor, we have 16 address lines. So how many registers it can address? We can have this by the calculation. So 16 address lines are there. We were having 2 raised to the power n equals to number of registers. This is the formula we have for calculating the number of registers a microprocessor can address. We have 16 address lines. N is the number of address lines, so we can have 2 raised to the power 16. So it is 65536 registers. So this many number of memory registers can be addressed using the 16 address lines of the 8085 microprocessor. Okay. Now how we can decide the memory range? Okay, that from which address to which address this microprocessor can address the memory. The memory address range of 8085, it starts from 0000H to FFFFH. Here H is showing that this notation of the numbers, it is in hexadecimal notation. So these are the hexadecimal digits. Okay, and the address of the first memory register, it is starting from 0000, and the address of the last memory register is FFFF. So in this video we are going to see that how these address range they are decided, how we can calculate this address range, and how the mapping of the memory is done. Okay. Now, what is the need of doing this? Why we are getting the addresses for every memory register? The address is required because we want to store the programs and data in these memory registers. And if we want to store, because there are 65536 registers, so how the microprocessor is going to understand that at that particular memory address we have to store the program or the data. So to point out that memory location, we need some address for that. Like take an example, if we want to go, we are going in a colony and that colony is having 1000 houses which are identical with each other. Now all the houses are identical, and how we are going to identify that house is of our relative, and we have to go to that house. So each block, how the society will organize those houses, it will divide those 1000 houses into blocks. Each block will have 100 houses. Okay, and each block will have a particular notation like 0 1 2 3 till 9. So there will be 10 blocks, each having 100 houses. Now in these 100 houses we can have rows. Okay, and each row will have 10 houses. So how we can recognize the house, that in which particular block that house is located, we will go to that block, and in that block in which row the block is the house is located, so we will go to that row, and in that row which number of house which we have to go. So let's understand it by making the diagram for it. This is our whole society, and this society is having 1000 houses. Now we are dividing these 1000 houses into blocks. So sorry, one block is extra. We have the 10 blocks here, okay, and we are naming all these blocks as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these are the 10 blocks, and each block is having 100 houses. Now these 100 houses, they are divided into 10 rows, and each row is having 10 houses in it. So suppose this is our 0 block. So in this way we have 10 rows, okay. So this is what our 0 block, and these are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 rows, and we have to go to this fifth number house, whose address will be like 0, 1, 1, 2, 3, 4, 5. So this house will have the house number 0, 1, 5. So 0 block, first row, and fifth number house. So in this way we can identify the houses which are identical with each other, and we can recognize it. So similar way is used to identify the memory registers and giving them the memory address. So by this memory address, the microprocessor will understand that on which page it has to jump, on that page which row, which column number that memory location is being located. Okay, so in microprocessor, addresses are assigned to each of the memory registers, and the microprocessor, it is having 16 address lines. So 16 binary digits, the address will be of 16 binary digits, and these 16 binary digits, they can have 65536 combinations, because 2 raised to the power 16, it is 65536, because we have the two binary numbers 0 and 1. So using these two binary numbers, we can have, and 16 binary lines, we can have 65536 combinations. So these combinations can be used to address the 65536 memory registers. So each memory register will have a particular and unique memory address. That memory address will not be shared by any other memory register. Each memory register will have a unique address, and using this address, the microprocessor can point out that memory register. Now these 16 binary digits, when they are converted in hexadecimal notation, they are equivalent to 4 binary digits. So in hexadecimal notation, so in hexadecimal notation, 16 binary digits are equivalent to 4 hex digits. So 16 bits of binary number, it can be converted to 4 bits of hexadecimal number. Okay. So if we have the address range, we were having the 16 binary digits, and we have the 65536 combinations. So these 65536 memory registers will have the address range starting from 0000H to FFFH. Okay, this is the address of first memory register, and this is the address of the last memory registers. How we can have this is, if we write it in the binary digits, it will be 0000 So this is a 16-bit binary number. The first address will be when all values are 0. So this address, these 4 will be equivalent to 1 hex digits. This 4 is equivalent to 1 hex digit. This 4 is equal to 1. This is equal to 1 hex digits. So in hexadecimal, it will be 0, 0, 0, 0. Similarly, if we have 1, 1, 1, 1, this is 1, 1, 1 and 1. All are 1. Then this is equivalent to F, this is equivalent to F, this is F, this is F. So the address we are getting is F, 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 H. This is the last combination which we can have. So the last address will be F, 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 F. So in this way, the 65536 registers, it will have the 4 bits of the hexadecimal number, or we can say 16 binary digits. Now let's take an example that how this address range is decided. Suppose we have a memory chip which is having 256 registers. Okay, now these 256 registers, we have total registers as 65536. Means we can point out till 65536 registers. The microprocessor have capacity to address this many number of registers, but the memory chip, the memory which is connected, which we want to connect with the microprocessor, it has only 256 registers. So how will be the address lines they are used? For these 256 registers, we can get the number of address lines by using this formula. We have 2 raised to the power n, n is the number of address lines, is equal to number of registers. So 2 raised to the power n equals to 256. So we have n equals to 8. So only 8 address lines are required to address this memory chip which is having 256 registers. Okay. Now total address lines available to the 8085 microprocessor are 16. And we are using only 8. So the rest of the address lines, they are connected to the chip select signal. We have studied in the requirements of a memory chip that every memory chip has a chip select signal which is used to select that chip. So the total address lines, we have 16. So let's write them. Now 8 address lines are used to address these registers 256. So we are using A0 to A7 for that. Okay, so A0 to A7, they can have any value between like they can have 0 or they can have 1. So first address will be when all are going to have the 0 value, and last address will be when all are having 1 value. So these are the 256 combinations of the two numbers 0 and 1 which can be used to address these 256 registers. Okay, so from 0 to 1 it can have any value. Now rest of the lines, they are used to address the chip select signal. Now chip select signal, it is the active low signal. So all the lines, they will have the value 0, 0, 0, 0, 0, 0 and 0. So they can be used to form the chip select signal. Now what is the address range? When the value of all are 0, 0, then combine them. You have to write the address range in the hexadecimal notation. So 4 bits are combined to form 1 bit in hexadecimal notation. So this is what? 0. These 4 are again 0. These 4 are again 0. And last 4 are again 0. So first address is 0, 0, 0, 0. Now last address, again A15 to A8 they are 0 and A7 to A0 they are 1. So these 4 0, these 4 again 0, these 1111, they are equivalent to F in hexadecimal notation, and last 4 they are also 1, so it is equivalent to F in hexadecimal notation. So this is the address range of this memory chip, which is having 256 registers. So in this way we can calculate the address range of a memory chip. Okay, so this address range is 000000FF. All you have to do is first identify that how many address lines you require to address this memory chip. Then out of 16 you have used 8 address lines, so remaining lines are connected to the chip select signal, and then check the address. Okay, let's take another example. We have a memory chip which is having of the size 1 kilobyte. Okay, now 1 kilobyte, it has 1024 binary bits. Okay, this is given to us and we have to find out the address range of this memory chip. Now we have to calculate the number of registers. So number of registers are, we have 1024. Okay, so 1 kilobyte, it is equal to 1024 bytes. So we have 1024 registers and it is equal to 2 raised to the power n. Now n is equal to 10. So 10 address lines are required to address this memory chip, and we have A15, now we are using 10 address lines, so A0 to A9 are used to address the memory chip, and A10 to A15 they can be used to select the chip, and A9 to A0 they can have value from 000 to 111. Okay, so combine all them, we have the 4 as 0 0 0 0 0 0. So these 4 are 0, then these are 0 0 0 0, so again 0, then we have these 4 and this 4. So first address is 000 H, last address will be 00004, we have 0, then 0011. So 0011 is equivalent to 3, because what it is 8421. This is what we have in the hexadecimal notation. So 2 and 1 are 1, so 1 and this 2 plus 1, it is 3. Then we have 1111, so it is F. Then we have 111 and 1, so it is again F. So first address of the first memory register is 0000 and address of last memory register is 03FF. So this is the address range of the memory chip, which is of the size 1 kilobyte. Okay. So let's if in this example where we have taken this memory chip which is having the size 1 kilobyte, if we want to make some change, like if we want that this A15 line, it is always at logic 1, because what we are doing here, these lines which are used to address the memory chip, they can have any value bit from 0 bit like they can have 0 or 1. They can have any of the two values, but these lines which are used to select this chip select signal, which are connected to this, they are always at logic 0, because this chip select signal, it is an active low signal. So these has to be at logic 0. Now if we want to have this A15 line as at logic 1, then this address range is changed. How? If we have this 1000, so this will become 8. in hexadecimal notation. Then we have this 0000, so it will be 0 and all are again 0. So first address will be 8000H, and if we have 1000 and then 0011, so it will be 83FFH. So you can see that the address range is changed whenever you change any of the logic level at these address lines. So you can change the address range according to the availability, that what you want, that if you want that the memory addresses it will start from 8000, then you can change the logic at the address line A15, you can make it at 1. So this address range will be used. Okay, so let's summarize all the topics, all the tips which we studied in this topic, the memory map and addresses. Let's summarize all the points. So in a numbering system, the number of digits which are used, they determines the maximum addressing capacity of the system. Like in the 8085 microprocessor, we have 16 address lines. So these 16 address lines can have 16 bits. So the number of digits, it determines the maximum addressing capacity. So 2 raised to the power 16 means 65536 memory registers. So the number of bits the microprocessor it is using, it determines the maximum addressing capacity of that system, that it can address this many number of memory registers. So for a given memory chip, the number of address lines which are required to identify the register, it is determined by the number of registers in the chip. How many number of registers are present in the chip, that will determine that how many number of address lines are required to address them. And the remaining address lines, they can be used to for the selection of the chip, that is to connect to be connected to the chip select signal. Then we have address lines which are used to select the register are the lower order address lines. You have seen that the examples which we have taken, we have always used the lower order address lines for the for pointing the memory registers, and the higher order address lines, they are used to select the chip. So the address lines used to select the register, they are the lower order address lines, and they can be assigned any logic level 0 or 1. And the address lines which are used to select the register chip are the higher order address lines, and they are at fixed logic 1. Okay, for that given address range. Then we have the The address range, it can be of a given chip, it can be changed by changing the hardware of the chip select line. Like the last example which we taken, where we have kept this A15 the most significant address lines, the highest order address line, that is the A15, we have kept it at logic 1. We have fixed the logic for that A15 line. So we can change the address range by changing the hardware of the chip select line. Okay, so these are the points which we have to keep in mind whenever you want to find out the memory address of a chip or memory mapping. This is called memory mapping, that how we are identifying the addresses of the memory registers of the chip. So I hope that this topic is clear to you. Thank you.